Okay, okay.
Znowu nam zniknął? Gdzie on? Widziałem, że brał jakieś te listówki. Porozmawia z Berlinem. A może na dole tam nie hali. Co tu jest? Jakiś te... Cyrkon. Tlenek
Hi,
cyrkonu.
hi or hello?
No.
Any questions?
I don't know right now. Could you tell us something about the process, the printer you have?
So we are focusing on multi-materials, really on combining materials for the purpose of combining their properties. Because for some applications, you can't just only use one. A good example of this is electrical functions. Because, for example, you need an electrical insulator and an electrical conductive material. An insulator could be a polymer or ceramic. Conductors are then likely more on the metal side. So, and then you will have to combine them. Single ceramic or single metal won't do. And then it goes into other property combinations. For example, this could be aesthetics. In this case, it's just its colors, right? So it's colored pigments. It could be something that is, for example, fluorescent or something where it's just like this kind of colors for aesthetic purposes. Then here, as I said, this is an effect of combining, for example, something like copper and glass, or here it's a ceramic, it's a zirconia, which you have as an implant material, or for like heat shield and rockets and all this kind of stuff. You use it in vacuum technology, anywhere where you need inert, high temperature stable, let's say surfaces or bulk material, and then you can combine this, for example, with a stainless steel like 316L or 74 pH. So you have electrical conductivity, you have the possibility to combine then the metal side of it again with other methods that usually you combine metals with, I don't know, welding or whatever, and so on. And so if you need this miniaturized, then it's hard to integrate, but here you can do it like this. It can be also bigger, it can be actually sized like this. The process is very simple in that sense. It's like injection molding. You have a thermoplastic binder, so like imagine you have a wax, you heat it up, it becomes liquid. You put the powder inside, that's kind of your printing material. There's a bit more magic to this. And then instead of injecting this into a mold-wise liquid, you put it into a print head, and the print head deposits it as a little drop. So now the powder, the metal, is still in that drop. And now you make basically layers out of this, and now the metal is in there where you ever need in your 3D build. If you want to combine it, then you have another print head with the ceramic powder inside, which then the ceramic powder is trapped in the drop. And now they are all together come into that layer, and the binder melts together and solidifies by cooling. Then the part is cool. You can move it and you debind the sinter as it is done in industry with injection molding forever. So, and this is basically how it works. And then sintering is the challenge, right? How do you combine the metal and so on? But you can make this happen. So we sell the machines, we sell the materials, and the printer also has it's not only building up, it also has a function with a laser. So one is building up, that I just explained. The other function is if you work with the hardest of materials, usually if they are sintered, if they are dense in the end, the surfaces, you still want to have very, very good surfaces. Then you will have to, mill, grind, polish, whatever, do this again. Usually with diamond tooling. And this diamond tooling, all of what you do is usually more expensive than anything that you did before. And so we have a laser inside which works on the green part. It can melt the binder, it can ablate the binder, it can suck the powders off. So instead of having, let's say, 5 micron surface quality, you get below 0.5 micron surface quality, RA. And so you save a lot of money and time. And this is actually the print side. I think this is very unique. So basically